Now, the past couple videos we've been kind of leading up to using the antiderivative to find area. Now we just call this integration at this point, but to find the area under the curve. And one thing we kind of glossed over is what's called the fundamental theorem of calculus part 1. The fundamental theorem part 2 is what tells us that we can use the antiderivative and evaluate it at endpoints to find the area under a curve between those x values, or those endpoints. But as I said, we kind of gloss over the fundamental theorem part 1, which is really just stating that this relationship between a derivative and an integral exists. It tells us that if a function is continuous, then if I set up a function to be the area collector, remember in a previous video we talked about a function's area collector, that a positive area makes the area collector increase, negative area makes the area collector decrease. If I define a function to be the area collector of little f, then the derivative of the area collector is equal to just little f. Essentially saying if I take the derivative of the integral, I just get the function out. So this establishes this relationship that the derivative and integral are essentially inverses of one another, and to find area, we simply use the antiderivative. So this fundamental theorem part 1 establishes the relationship that fundamental theorem part 2 uses to find the area. Now I just want to go through one example, kind of in a long form of how this works, and then I want to show you some shortcuts. So let's just really quickly do this kind of long example. I'm asking you to find the derivative of the integral from 0 to x of 1 over 1 plus t squared. Well, I'm going to just start by focusing on the integral. And I'm going to continue to leave this derivative thing outside, but let me start by just evaluating the integral. Well, the antiderivative of 1 over 1 plus t squared is the inverse tangent of t. You may not remember that from a couple chapters ago, but that is the antiderivative. Well, now what do? I plug in x and 0, right? That's what you do with an as you're evaluating an integral. So the inverse tangent of x, the inverse tangent of 0, and we subtract. That's what we do with an integral. We find the antiderivative and then plug in the endpoints. Well, at this point, I can take the derivative because I'm done with what's inside the brackets. I certainly could have evaluated this. The inverse tangent of 0 is 0, but I'm just going to stop there for now. So now I'm going to take the derivative. Well, the derivative of inverse tangent is 1 over 1 plus x squared. Well, this right here is a constant. I'm just going to put C-O-N like that. It is in this case 0, but it doesn't matter that it's 0. It's a constant. And the derivative of a constant is 0. So my final answer ends up just being 1 over 1 plus x squared. So if I took the derivative of the integral, I ended up with the original function, just instead of a t I had an x because I had substituted the x in. Well, that's exactly what fundamental theorem part 1 said would happen. If I take the derivative of an integral, I end up with the function back with an x instead of a t. So let's exploit this to do some of these a little short. I guess maybe let me do one more kind of long way, but again I'll do it pretty quick. Derivative. Well, the antiderivative of sine is negative cosine t. We're going to evaluate at x and negative pi. Okay, so we have negative cosine of x minus negative cosine of negative pi. Again, we're going to take the derivative. So again, I just found the antiderivative, I plugged in x and negative pi. Okay, I should put maybe some parentheses around that. Well, the derivative of negative cosine is sine. And again, the cosine of negative pi is negative 1, so this whole thing in here is once again a constant. And the derivative of a constant is 0, so the answer is just the sine of x. So again, I got the original function back out with an x instead of a t. This will always work as long as the lower bound is a constant and the top bound is an x. So this next problem, maybe I can shortcut a little bit. The derivative, d over dx, it goes from negative 1 to x plus t cubed. Instead of actually going to the work, why can't I just say, you know what, it's going to come out to be 1 plus x cubed, and I'd be done. Now, one thing I should mention, if I did like 2 to x of x, let's use t. I'm going to use the right variables here. And I'm doing the derivative. Hopefully you can pick out right away that this would come out to be x squared. If I change this constant to, I don't know, like a 5, it's still going to come, the answer will still be x squared. Okay, but let's say I did this. Okay, let's say that I went from 2 to x. Well, normally I like the bounds to the bottom bound to be the number and the top bound to be the x. I switched them, so all I need to do is change the sign. Now here, you notice that what I changed was that the top bound isn't just x. So let me go through again a long one. Do it the long way, and then you'll see real quick, I think, what the shortcut will be. So I'm going to take the derivative. Okay, I'm going to leave that. The antiderivative of cosine is just sine. I plug in x squared, so I get the sine of x squared minus sine of 1. Remember, I'm going to take the derivative of that, so I better write that out front. Okay. Well, sine of 1 is once again a constant. Okay, just do that. So the derivative of that will be 0. The derivative of sine of x squared, though, we're going to have the cosine of x squared multiplied by 2x. And if you recall, this is chain rule. When we substituted this bound in, and then found the derivative, we had to do the derivative of the bound. Well, this is different. We haven't had to do that before. But in a way, if the bound was just x, okay, like before it was just x, the derivative of x was just 1. So, I mean, you could think about it that you're always using chain rule, that the derivative of the top bound just happened to be 1. So now we're a little bit different. Instead of, before we just said, well, I'll just replace the t with an x, now we replace the t with that bound, so cosine of x cubed. But then we have to multiply by the derivative of that bound because of chain rule. So derivative of cosine is negative sine. And that's it. Okay. So we, it's a little bit more work, but not terrible. Here, we replace the t with an x cubed. This becomes x cubed cubed. Then we have to multiply by the derivative of the bound, which is 3x squared. Be very careful with your parentheses here. Make sure you're putting your function in parentheses. I'll oftentimes see people say, okay, it's 4x to the 9th plus 5 times 3x squared. This is not correct. Okay, that's not right, because 5, that makes it look like only the 5 is being multiplied by 3x squared. That's not the case. The entire function needs to be multiplied by the derivative of the bound. This is Fundamental Theorem of Calculus Part 1. Again, this establishes the relationship that we use in Part 2 to find the area under the curve. That relationship that the derivative of an integral is equal to the original function.